Yeah, thank you, and thank you for having me here. Yes, I will be talking about multi-physics modeling in PPE. So PPE, as all of you know, has become much more important in the last several years, but a lot of PPE technology is based off of filtration, where you're forcing air through a filter and removing pathogens. This includes N95 masks and also other recent devices like the Dyson Zone. Now, one thing that people notice immediately is that filtration greatly impacts the breathability of these masks. So there's other alternative approaches that people are trying to come up with, including UV-based PPE. Now, UV, it doesn't impact breathing, and what I mean by that is that if you breathe through a device, it's going to feel the same whether the UV is on or off. It actually treats the air rather than just removing parts of the air, or particles in the air. And it also can be used for treating against possible unknown future microorganisms. Now, when you're modeling disinfection in PPE and in general, one of the ways that you model that is to generate a fluence rate field. Essentially, what's happening is that you're looking at the light source and you're determining at a location relative to that light source how much power is being delivered to that location. And then you use that coupled with fluid dynamics to be able to determine how much dose is actually being delivered there. A lot of past models include discrete ordinate models, multi-point source summation, and there's several others. They all have different uses where they're more or less accurate, but a lot of them have been developed specifically with water treatment in mind as opposed to air treatment, which is what we're looking at here. Now, when you're modeling disinfection, this is where the multi-physics comes in. You have the optical UV modeling, you have computational fluid dynamics, and you have inactivation kinetics. And you have to combine all of these things to be able to determine how much disinfection is actually happening. Now, a lot of these methods have been developed for water, and sometimes those methods are applicable to air. Computational fluid dynamics, it doesn't matter if the fluid is water or air. But when you're looking at UV disinfection and UV fluence rate fields, a lot of the past methods were developed for water, which has a transmittance of maybe 70 to 90%. This figure comes from a recent paper where they've looked at how does the reflectivity of the material, the walls, actually impact disinfection, and they found that for water in the 78% range, you didn't see any impact. But as you go up to 98% where you have the transmittance of air, you start to see multiple orders of magnitude impact on disinfection. As I said, past methods were made for water, and with these systems you have high photon recycling, so you need to have a method that can follow those rays, follow the system, and actually see what happens when light rays are reflecting multiple times. So one way that's become more developed recently is optical ray tracing, where you are actually randomly generating light rays from the source, and you're following those rays throughout the system until some kind of termination criteria. Now, optical ray tracing is a relatively new method, and one thing that you want to do is you want to be able to check how accurate is this compared to real-world systems. So we were comparing against an integrating sphere, which is essentially a sphere that you have one port that has a lamp in it and one port where you can take a measurement. And the reason we want to do that is because we can calculate exactly what that measurement should be using Sumner's principle, which is listed here. And we can compare that to our method to actually determine the error, determine what different numerical inputs, how those change the error. Specifically here, we were looking at things like the solid mesh discretization. So essentially, how well does that computer image represent the real system? Is it going to look like a sphere, or is it going to look like a disco ball? We looked at how many rays we were randomly emanating, and we were also looking at the number of ray interactions, because we can't follow a ray forever. We don't have the computational resources, and we wouldn't want to. So we tell it, okay, we don't want to follow that ray after 100 interactions, after 100 reflections, or 1,000 reflections. And we looked at all of these things and saw how does that impact the error using Sumner's principle. Now, what we found was that ray tracing follows Sumner's principle pretty well. You can see the analytical solution versus what we computed from simulations. Now, there was a slight residual throughout, but this was likely, it could be due to the method converging to a slightly different result, or it could be due to the solution being developed for a perfect sphere, which this isn't. But one thing I want to point your attention to is how the actual average irradiance grows exponentially as you increase the reflectivity. So essentially, as you're getting more reflections that are significant within that system. And you can even get up to 21 times at 99% reflectivity versus at 80% reflectivity. And so if you look at different materials, you can look at aluminum, which is around 78%, 79%. Polished aluminum goes up to 85%. And then you get into the Porex materials, which I discussed a moment ago, that are PTFE-based materials. And you can get up to 99%. You can get up to 98% reflectivity with PMR20. I believe they have a 99% material that they've been discussing. So now that we have a good sense of how the UV modeling works, we moved on to a test reactor that was kind of a first iterate, a proof of concept. And this here, this is the Nichia reactor, which had 4 Nichia LEDs shining into a PVC pipe, essentially. And that pipe was lined with PMR20. And this is the computational design representation. And compared to the actual measurements that were taken, we compared pretty favorably. Now, this is the different results for the different physics that are involved, the fluence rate field, the velocity field from the computational fluid dynamics, and then the particle tracks, which were used to calculate dose. One thing that I would like to emphasize is that with the highly reflective material, this is weighted by the average irradiance, the average fluence in the reactor. And you can see that there's a very nice even distribution within that reactor, as opposed to if you don't have reflective material, you're going to get hotspots around the lamps and you're not going to see that extend outward throughout the reactor. And that's really what you want to get when you're trying to design these systems. As the reflectivity was increased, the average fluence increased as well exponentially, although it didn't quite reach the levels that the integrating sphere reached. What we saw was that there was a lot of light escaping out the open ends, and so we were still getting about 7x irradiance, which you could roughly relate to the disinfection potential of the system. So we moved from that over to another prototype that essentially used what we learned from the first prototype, and we included optical baffles at the ends to allow the fluid through the system, but also have more photon recycling. This is actually the system that Jason discussed in the last presentation. This was what was inside the pod reactor. So we actually have experimental data for this reactor. And we used a Ushio lamp inside of it and 97% reflective material. And we were really looking at a 90 liter per minute flow rate through this system. The reason we did that is that would be maybe the highest instantaneous flow rate that you might see during elevated breathing, during maybe exercise. And we wanted to make sure that even at that elevated flow rate, we could get good results. And you can see that here as it flows from the bottom of the reactor up through the zone where you're going to have disinfection, and then back out through the top where you're going to have delivery to the person. And to determine the dose distribution through this system, we used particle tracking. Essentially, we randomly introduced particles at the inlet and followed those particles throughout the system and actually tracked how much dose, how much fluence was being delivered to those particles. And here's a figure that shows you the different irradiances throughout, and you can see that there's a very even distribution throughout the system, similar to the PVC reactor. So looking at the dose distribution, we had a minimum dose at this highly elevated flow rate that was greater than 2 millijoules per centimeter squared, which is about a little over 2 log inactivation for SARS-CoV-2. And that's, we calculated this by using the resonance time and the delivered fluence to each particle as it passed through the system. So with that, we were able to use numerical modeling to quickly iterate through several different reactor types. We essentially started with a concept that high photon recycling could greatly impact the disinfection potential of the system. We moved on to a simple proof of concept where we could introduce flow into the system. And we used what we learned here to be able to move on to a much more complex prototype. And we used this complex prototype as the basis for the lovely prototype that we have out in the hallway that you can see after this. So with that, I'd like to thank my contributing authors. Especially, I would like to thank Christopher Jones, who's the other modeler on our team, and Dr. Joel Ducoste, who's advised me on this work. And I'd also like to thank our project sponsors. And I'll take any questions that you have. Yeah, so the question was about how humidity would impact the efficiency of the system. I would say that it'll certainly impact it. All of these simulations were carried out assuming essentially perfect transmittance. You would see less dose delivered, and we would generally account for that using a safety factor, although we are developing methods to be able to introduce some humidity and introduce droplets. It does have an impact, and it's tricky to introduce both numerically and experimentally. It would basically decrease it, but we don't expect it to decrease that much.
Did you design any kind of sensor to the lamps to see if there is a decrease in power or any change?
Yeah, so the last presentation was given by my colleague Jason, and he discussed an MFSD sensor that essentially measured the reaction to UV, and that's what we compared to when we were doing experimental to simulation comparisons. Yes, this was why we designed this system specifically, is because we were able to get the sensor inside the system and be able to look all throughout, but in the final prototype we didn't include a sensor. Yes, so with this dose distribution, if you're looking at the minimum dose, I believe that's on the order of 2 log inactivation, so about 99% inactivation. Now this dose does increase, and if you looked at the average dose, you would get a larger inactivation, but we were designing for worst case scenario, so we really took the lowest dose when we were evaluating different light sources and things like that.
This is a great presentation, thank you. Are these distributions in terms of like normal distributions or log normal? Or can you elaborate a little bit on your observances of that?
Yeah, I don't believe that this is a normal distribution, although I think it would probably be a log normal distribution when you're looking at that. Oftentimes when you're looking at flow through a system and you're talking about, say, species transport, which you can really treat the viruses as something that's microscopic, that's transporting through the system, you usually see a log normal distribution of particles and things like that. So that would be my guess. I haven't actually done that analysis with this data, but that would be my expectation.
For example, in the disinfection for the water, for the drinking water, we need 40 millijoules per centimeter square. But for this, so is there any required dose?
We were really looking at 2 millijoules per centimeter squared, and that was based off of data that was done by Chip and Carl's team, I believe. but there was some, I believe it's at this wavelength that we're working at, which is 254 for this lamp, or possibly 222 with some of the other designs that we've been doing. You don't need quite as high of a dose. And it's also likely due to the different transmittance through the system. So in water, you're going to look at 70% transmittance versus air, which has maybe 98% transmittance. So if you're thinking about how much dose is actually, how much power is actually delivered throughout the system, it's going to be less in water versus air with each light source.